G'day viewers. In this segment we'll talk about the fairness of a bandwidth allocation. So our topic is really the question of what's fair anyhow? What does it mean for a bandwidth allocation to be fair? And in particular we'll talk about the max-min fair allocation. So just a little bit of context before we dive into fairness. We've talked about trying to solve the problem of bandwidth allocation to give different senders bandwidth through the network to communicate with their receivers. We want any allocation that's good to be both fair and efficient. Efficient we talked about when we covered congestion, and we talked about using all of the network but not operating in a congested state. Fairness I didn't really explain. I just said that all senders should get some reasonable share of the network. What exactly does that mean? That's a pretty vague statement. Now, in this segment, we'll learn what it really means to be fair. And I'll give you one caveat while we go into this, and that is that fairness in networks, as in life maybe, is overrated. In practice, it's going to be more important to use the network efficiently than it is going to be precisely fair. Fairness will still matter in some sense, but not at a very high level of precision. Okay, so we have these two different considerations, efficiency and fairness. One of the first things I want to tell you is that they're sometimes in conflict. It's not clear that we could always have both. That's one bit of bad news. Consider this example network. Now here we have three hosts shown in the picture, A, B, and C, and we have three traffic flows. One is simply going from A to B over this link, which has capacity of 1 unit. One's going from B to C over this different link, BC. Again, it has capacity of 1 unit, and one flow is going all the way from A through B to C across those two links. And to solve the bandwidth allocation problem, we need to decide how much bandwidth, how much traffic we will allow to go along each flow. Well, suppose we care about fairness. What should we do? We could simply give all of these flows an equal amount of bandwidth. That way they'll all be treated the same. If we did that, since the limit is 1 unit across each of these links, the best we can do is assign a half unit to all of the different flows. A half to AB, a half to BC, and a half to AC. Because if we do that, you can see that the flow AC goes through B, so we'll have half a unit across each of these links. When we sum it with the other flows, we get up to the total of 1. So in this way, we're actually using all of the network. We've used all of the capacity on both links. Everyone's got the same amount of flow. So we've certainly been fair. In this case, the total amount of traffic that the network carries, which is a measure of its efficiency, is 1.5 units, 3 halves. Okay, well, what if we care about efficiency? If we care about efficiency, this is what we would do. We would want to maximize the total amount of traffic that can go through the network. That's our measure of efficiency. Now, just by inspection, I can see that we can increase the traffic going through the network by simply assigning 1 whole unit to AB, 1 whole unit, that's one, to BC, and nothing, 0, to AC. In this way, we are able to to grow the total amount of traffic through the network to be 2 units, 1 plus 1. That's bigger than 1.5. So we're operating the network more efficiently. Really, we've done so by penalizing AC. That unfortunate flow happened to go through 2 links, so it was kind of competing a little more for network bandwidth than the other flows. And so if we just set it to 0, and give the bandwidth to the other flows, we can send more traffic through the network. So you can see that fairness and efficiency can leave us at different points. And nonetheless, we're going to want a little bit of each of them and not go to the extreme of caring about efficiency and not caring about fairness. Now, it's actually a little worse than I've been letting on so far, because not only are fairness and efficiency in conflict, but it's not clear what we really should mean by fair. I said equal per flow. Okay. Why is that fair compared to other things? For instance, really the reason that there was a difference in our allocations between the first fair one and the next efficient one is that this flow, AC, went through two links, so it was using more of the network resources than the other flows. Why should we give it the same amount of bandwidth then? Maybe since it's using more network flows, it should be penalized more, and we should give it a third of a unit and give the other flows 2/3 of a unit, because then everyone will be using the same sort of amount of packet hops or something across links. In addition, so that's one consideration for fairness. In addition, we could look from a host point of view, not a flow point of view. Host A is actually getting to send 2 flows worth of traffic. So host A is sort of getting to send twice as much traffic if we give an equal amount per flow than host B. Well, that doesn't seem right either, so it's not fair in that sense. So as you can see here, fairness is a pretty slippery notion, and it's not clear how we should best define it. Now, I'll also tell you what I'm sort of arguing about this fairness and efficiency is that what we really want to do is avoid starvation. So that allocation for efficiency where AC didn't get to send any traffic at all is not desirable, because we're precluding that flow from using the network. It should be able to use the network to some extent. It turns out that it's really not terribly productive to argue about exact notions of fairness and differentiate between them. And we'll stick with our equal per flow. You can see that there are potentially some problems here, but approximately equal per flow is generally going to be good enough, and that will certainly avoid this starvation problem. Okay, so equal per flow it is. I'd now like to tell you what equal per flow means in a more complicated network setting. We looked at a very simplistic example, and it turns out that it's a little hard to generalize from that example to what equal per flow means across a network. I'll tell you why. So let's start out with a little bit of terminology. The bottleneck for a flow of traffic is the link which is limiting the bandwidth. So for instance, if I have that flow, this is going from A to C through this network, it's going across 2 different links. Now note I've changed the capacity of one of the links in this network so that it's 10 units. It's a fast link. The former link between A and B is still slow at 1 unit of capacity. For this flow, AB is the bottleneck link. It's the place that's limiting the amount of capacity we could assign to this flow, and it's also the place where congestion is going to occur. That link is going to be congested. So the link AB is congested, meaning that the queues will build up just before it in A, trying to get on to the network. So that's what a bottleneck is. In examples which are more general than the first one we looked at, you'll note that different flows can have different bottlenecks. That is, different flows can be limited by different parts of the network. Here we looked at the other flows in the example. If we look at AB and BC, they go over different sets of links, they're disjoint, so they're going to have different bottlenecks. For AB, the bottleneck link is literally that link AB. It limits the flow to 1 unit of capacity. For BC, it only goes over 1 link, so that's the bottleneck link. But that link limits the capacity to 10 units. So it's different. It's a different place in the network, and it's a different amount of capacity we have that is at the bottleneck link. So it's no longer possible to have a very simple picture where we evenly divide the bottleneck resources amongst flows. We need to do something a little more general than that. And the more general allocation that's going to give us equal use by flows at the different bottlenecks is something called max-min allocation, a max-min fair allocation. It's going to be an allocation that maximizes the minimum that flows get. This is why it's called max-min. Now, intuitively, to generalize our equal per flow allocation, we could describe it in this way. All flows that are bottlenecked at a particular place in the network should get an equal share of that bottleneck link. That's what our max-min allocation is. This definition is a little circular though, because bottlenecks are caused when different flows send different amounts of traffic. That's what causes a link to be full and reach capacity and a bottleneck to appear. So we can define a max-min fair allocation in a way that's less circular, but is a little puzzling, like this. A max-min fair allocation is one in which increasing the rate of one flow must decrease the rate of a different flow which was already smaller. Wow, that's a little tricky. But if you come up with a point which has that allocation, then it will be the case that you have maximized the minimum flow. And then for the second smallest flow, you've also maximized what it can get out of the rest. And for the third smallest flow, you've then maximized the amount it can get out of the rest of the network, and so forth. We're going to look at an example, and that will hopefully make some of this strange concept just a little clearer. So I defined a max-min fair allocation in a bit of a puzzling way. I didn't tell you how to find that allocation. Here's a procedure you can use to find that allocation. It's a pretty intuitive one. You just imagine we have all of these flows going through the network, each flow from a source to a destination. Just imagine pouring water into the network along these flows, raising the level of all flows, and we'll see what bottlenecks they run into. That will help us find a max-min fair allocation. So if you start with all of the flows with rate 0, then you pour water along the flows by increasing the rate until you run into some bottleneck in the network. Now, whoever is part of that bottleneck, you can't increase them anymore, so hold their rates fixed and go back and increase the rate of any other flows which are not bottlenecked until they find a new bottleneck which will appear. Then subtract them and increase anyone who's left, and so on. We'll look at an example just to see how this works in practice. So here we have a network. There are 4 flows. For example, we're going to call them A, B, C, and D. The A flow is really sending from A on the left to A on the right. The B flow from B on the left to B on the right. But you can see these different flows go through different links. So they might potentially have different bottlenecks. We'll assume here that every link has the same capacity. We'll just call it 1 unit. Okay, so let's imagine we want to find the max-min fair allocation. So we start pumping water along all of these flows and raise the level. They start at 0, a tenth of a unit, 2/10 of a unit, and raise. And what's going to happen? Well, as soon as we get to 1/3 of a unit, flows B, C, and D will fill up this link here. Let's just move ahead. Here it is. So now everyone, A, B, C, and D, is sending at 1/3 of a unit, and we bottleneck this link here. This means that we can no longer increase flows B, C, and D. They're fixed. There are, however, still flows left. The only flow that's left is A. So we will keep raising A until we reach another bottleneck. How far can we raise A? Can we raise it at all? Well, actually, there's a little bit of spare bandwidth left on this link that's not used. It's at 2/3 of a unit, so there's a little left over. So we're going to raise A, and what will happen? We will reach this point. We can raise A until it has a rate of 2/3 of a unit of flow. When that happens, we'll be bottlenecked on another link. And then A can no longer increase. And there are no flows left, so we're done. We have an allocation. Here's what the allocation is that we ended up in, just to remind you. A had 2/3 of a unit, B, C, and D had 1/3 of a unit. So you can see, even though it's equal per flow, not everyone's going to get an equal amount. Now in this allocation, 2 links were maxed out, between R4 and R5, and between R2 and R3. Some of the other links had unused capacity. That capacity simply couldn't be used in the network while still having a fair allocation. I'll just write down what it is so you can see it. Just looking between R1 and R2, we have 1/3 of a unit of excess capacity that's not used. Between R5 and R2, we have 2/3 of a unit. So we're really not using that link very much at all. In fact, if we were building that network and we had this traffic flow, we could maybe make that one slower and it wouldn't slow anything down. And also between R5 and R6, we have 1/3 of a unit that's left over in our network. So this was as efficient as we could make the network while still making it fair according to max-min fairness. And finally, just for fairness, I want to point out that the fair allocation will change over time. Before, we considered a fixed picture and we were just trying to maximize the flows individually. But in this picture, let's look over time, as time goes along, to the right, what happens to the bandwidth allocation. So you can see here just an illustration of how bandwidth allocation can change over time. The beginning of time, flow 1 is the only flow that's actually using the network. So it's going to get 100% of a link. Just imagine these flows are all going over a very simple network. At time 1, flow 2 starts. So that means that flow 1 and flow 2 are going to share the network. Flow 1 will get half a unit. Everyone goes on. At time 4, flow 3 starts. Now flow 3 gets a small unit of bandwidth. We don't know why. Maybe it's bottlenecked somewhere else. Maybe it just doesn't have that much traffic to send. But at any rate, that means since it's using less than its fair share, if it was using the same link and it wanted to send more, flows 1 and 2 are going to divide the bandwidth that's left. So flow 1 will get now a little less. Flow 2 will also get the same amount. And they're going to go on until something else changes. What changes in this case? Flow 2 stops. In that case, flow 1 will take up the slack of flow 2 so that we have an allocation which is as efficient as we can, uses as much of the network, but is fair. For some reason, flow 3 is just limited to this amount, maybe because of a different path. And there we have it. Okay, so I've just cleaned that up. So now we know what a max-min fair allocation is, and fairness in allocations. We haven't yet looked at mechanisms which will find in a network when senders operate independently, which will arrive at a good bandwidth allocation. We'll go to that next.